So hi guys, welcome to the Central YouTube channel. Today in our physics series, we'll be discussing elasticity. So this is one of the important topics in physics because you ought to see them in your JAMB examination and in your WAEC examinations also. So make sure you like this video, share this video with your friends, and also subscribe to this channel also. Matter have three states, okay, which is namely the solid, the liquid, and the gases. These are the three states of matter. Nice. So the particle of solids are packed together more than that of the liquid, which are packed together more than that of the gases. So if these dots denote the particles of these states of matter, you can agree with me that the particles of solids are more packed than that of the liquid, and the one of the liquids are more packed than that of the gases. Nice. So if we focus our attention on that of the solid, okay, the particles of the solid have a great intermolecular force that binds them together. This intermolecular force tends to resist a change in the shape of the solid. There are some maximum forces that when you apply them to solid, the shape or the length of the solid gets to be distorted. Okay, so these forces tend to either elongate or reduce the shape of this solid. Once this compression force or this displacement force is applied to a solid, and that solid tends to go back to its original shape, okay, that denotes elasticity. So for example, if this is a bar, okay, this is a metallic bar, and you compress this metallic bar, once you remove that compression force and this metallic bar tends to go back to its original length, okay, you can say that this elastic bar is elastic. Nice. So elasticity is the ability of an object to go back to its original shape once the distortion force is removed. Okay, I'll give you an example. Okay, so this is a solid, okay, and this is normal length of this solid. So if I apply a displacement force this way to this solid, okay, if I remove the applied force and this solid tends to go back to original position, you can see that this solid is elastic. So I've removed the applied force and the solid went back to its original position. Okay, I apply my force again, I remove the force, okay, so the solid is going back to its original position. So you can say that this particular object is elastic. Elasticity is the ability of objects to go back to its original shape or position once the applied force is removed. For the scope of this topic, we'll be discussing this topic based on three major subtopics also. We'll be discussing the Hooke's law. We'll be discussing the Young modulus. And last we'll be discussing work done in elastic strings. Nice. So we'll begin with Hooke's law. So Sir Hooke, okay, carried out an experiment. In the experiment, he compared the extension of a particular object, okay, in relation to the applied force. So in his experiment, he compared Nice. So this young man, he carried out an experiment to compare the relationship between the applied force and the extension to an elastic material. That's a law, and that law postulates that the load applied to a particular object, okay, is directly proportional to the extension, provided that the elastic limit of that object is not exceeded. Okay, the law postulates that the load or the force applied to a particular elastic material is directly proportional to the extension, provided that the elastic limit of that particular object is not exceeded. Nice. So in his law, what he was trying to explain is that if this was an elastic material, nice, and you apply a force here, okay, this is an elastic material, and you apply a force, say the force is 1 kg or 1 Newton, okay, and initially here we'll have 45 meter of elastic material. So if you apply 1 kg or 1 Newton to this 45 meter of material, and if you remove this particular weight now, okay, if you increase this particular force now to say 2 kg or 2 Newton, the length of this particular initial material is going to increase, okay, say from this 45 to 48 meter. So what it means that if the length is increasing, if the length is increasing, that's if the extension is increasing, okay, the weight is also increasing. So once you progressively increase the weight of that you apply to a particular elastic material, the elastic material will be further extended. So this law postulates that the increase in force, okay, is directly proportional to the increase in the extension of that elastic material. If the elastic material, the extension is increasing, okay, the force is also increasing. So once the force is increasing, there's also an increase in the extension of the elastic material. Okay, in Hooke's law, okay, in Hooke's experiments, nice, he compared some known weights or some known force in relation to extension of elastic material. So he plotted a graph. Okay, he compared to the two data from extension of elastic material to the force applied in the elastic material. So he got a straight line graph. Nice. So if you plot a graph of extension of an elastic material to the applied force, okay, you are supposed to have a straight line graph. This straight line graph denotes, or this straight line graph postulates that the relationship is directly proportional. Nice. So this is our initial point. If you further increase the force, okay, in the elastic material, up here, you're going to have some curves. So say here is O, this point is P, this point is E, this point is Y, this point is B. If you extend your graph further, okay, once you exceed the elastic limit, the graph is not going to be a straight line graph again. So you're going to have curves this way now. Nice. Curve will lead us to the regions of this particular diagram. So in this particular diagram, you are going to find up to 3 or 4 regions now. So we have the OP region, and lastly, we have the EB region. You have the from O to P region, and you have from E to B region. Nice. So also this P and this E, they are different parameters, which we are going to explain also. So this P stands for proportionality points. Proportionality points. Okay. This E stands for elastic limits. This Y stands for yield points. Why this B stands for breaking point. Breaking or fracture point. Nice. So OP stands for elastic region, while EB stands for plastic region. So these are the different parameters that you can coin out from this diagram. Nice. So we'll be explaining all of them now. Nice. So like I told you before, this particular straight line graph, okay, this is where this particular relationship obeys Hooke's law. Okay, so from here to here, the extension of that particular elastic material is directly proportional to the applied force. Nice. But once you exceed here, okay, it's no more obeying this particular law. Nice. So let's talk about the elastic limit first. Now let's talk about this point E. In point E, the elastic object, okay, has taken much points, and beyond this point E, this elastic object cannot return back to its original position. Okay, you know, when I give you the definition of elastic objects, okay, these are objects that can return to its original position once an applied force is removed. Nice. So beyond this elastic limit, okay, after this elastic limit, okay, beyond this elastic limit, this particular object, say object AB, okay, the elastic object AB, beyond this elastic limit, this particular object AB cannot return to its original position. So beyond this elastic limit now, this young man loses its elasticity. Okay, beyond this point E, okay, this object AB will lose its elasticity. Nice. So that's the elastic limit, the limit of elasticity. Okay, the point beyond which this object will no longer be an elastic object again. Okay, nice. So we have y. Y is the yield point. The yield point. Nice. So at point y, okay, this elastic object AB has yielded all its elastic properties. Okay, at point y, this particular elastic object has yielded all its elastic properties. Okay, there's no more elastic power in him again. So beyond the point y, okay, he's no more an elastic object. It turns to a plastic object. Okay, beyond point y, beyond this point, okay, from here it becomes a plastic and no more elastic. Nice. So B here, B stands for breaking point or fracture point. Nice. So in point B, this particular elastic object AB, okay, has taken the maximum load he can take. The maximum load he can take. So at this point, he's like, I not do again. So at this point, this particular elastic object is going to break. Okay, it's going to fracture, it's going to break out, it's going to shatter. Okay, if you can use that word. Nice. So at point P, this is the breaking point. So here, this particular elastic object has taken the maximum force it can take. Nice. So with these explanations now, the regions can now be made more clearer now. So we have two regions basically. You have the elastic region and have the plastic region. So from here to here, this P is the proportionality point. It means that at this point, okay, these two factors, extension and force, they are still proportional to each other. So at this point P, the point P is now called what? The proportionality point. So from O, this point O, the origin, to this point P is called elastic region. So from here to here, this region, okay, is where the object is still elastic. Nice. But from this point E to point B, okay, as the plastic region. So, okay, this is the diagram or this is the correlation between extension and force or applied load. Nice. So, according to Hooke's law, okay, Hooke's law says that applied force is directly proportional to extension of a particular elastic material. Nice. So, it means that mathematically, applied force, okay, when you apply a force in an elastic material, it is directly proportional to extension of that particular elastic material. Okay, so the amount of force will determine the amount of extension, how the elastic material will extend. So F is directly proportional to E. Nice. So to remove this proportionality sign, F is equals to KE. Nice. So K is a constant called the elastic constant. Okay, or stiffness constant. Okay, so K is equals to this. Nice. So this K is equals to F over E, which is equals to, because if F, the force being in Newton, nice, and the extension being in meter, okay, so here we have Newton per meter as the unit. Okay, nice. So this is the mathematical representation of the Hooke's law. Okay, so this constant is equals to F over E, force over extension, and this is the unit.